Hey guys, I have your notes here for section 10.3, day 2. Before we get started on your notes, take out that huge post-it note that I gave you for a list of fun facts. We're going to add a fun fact to it today. And something you're going to need to know today is the fact that, trying to eliminate the glare, is the fact that for any constant x, the expression n plus 1 factorial outstrips x to the n plus 1. And here's what I mean by outstrips. It grows faster. So what that means, if I look for large values of n, this works for any constant x. For large values of n, this is growing way faster than this. N plus 1 factorial is growing faster than x to the n plus 1. Which means that when I make a ratio like this out of them, my ratio is headed toward infinity. Likewise, if I turn my ratio upside down, as n gets large, if I compare x to the n plus 1 over n plus 1 factorial, this denominator is growing way faster than the numerator, and so my ratio is headed towards 0. All right, put that down as your fun fact. Now, what we're going to be doing today is looking at errors in our polynomial. And, how do I say this? Be patient with me because I'm just not confident in my knowledge about error bounding. So I'll do the best I can. I just might trip over my words a little bit, so just be patient with me. So basically what we're doing, we have a function f of x. We're mimicking it with a polynomial. And remember, we start somewhere and we kind of work our way out. So a lot of them start at 0, like the Maclaurin polynomials, they start at 0 and we kind of work our way out. The more terms you have, the better match it is for a bigger interval. We're going to be looking at the error on that. So when I go out, I don't know, so far, we're not talking way out. When I go out so far, how much is my error? How much off might I be in my polynomial from my real function? That's my error. How much off might I be from my real polynomial, from my real function, using the polynomial to mimic it? So the first the first error bounding that we're going to do can be used with an alternating series. So if you look at your list of your Taylor series, you've got several alternating series on here. So this error bound can be used for any alternating series. So here's the premise. Whenever you cut off your polynomial, you say, I'm going to stop it here. The leftovers, the error, the amount that you have cut off will always be less than the next term that you would have included, but you didn't. And so here's a really cool, simple example to show you. Natural log of 2 can be expressed using one of our functions that has a nice Taylor polynomial with it. So we have a nice function, it's called natural log of 1 plus x. And we want this to represent natural log of 2, so I've put a 1 there. So I subbed a 1 into my Taylor polynomial, and these are the values that I get. This is a way to approximate natural log of 2. The farther out I go, the better approximation it's going to be. Okay, so let's stop it somewhere. Let's cut off our series and turn it into just a straight up polynomial. I want to cut it off kind of early so that I'm dealing with numbers that make sense to you. So what happens if I cut off the polynomial here? Let's look at the amount that I am disregarding. the amount that I'm disregarding, if I check out the next term is 1/3. My error, the maximum error, the biggest difference between my function and my polynomial will not be greater than 1/3. And here's why. If I look at 1/3, add the next two terms together. If I add the next two terms together, I get -1/20. Add the next two terms together, I get -1/42. And so on and so on. If I keep pairing those two terms, I keep adding these tinier and tinier and tinier negatives to this, my entire series that I cut off is going to be less than 1/3. So alternating series error bound says wherever you cut off your series to turn it into a polynomial, your error will always be less than that very next term that you left out. All right, the next error bound is called the remainder theorem. It's not called the remainder theorem. That's totally pre-cal. Apparently it's the Lagrange error bound. So what we have here, here's our function. Here's how we make a polynomial. We find f of wherever, and then we find our derivative there. And this is over 1 factorial, and this is x minus c to the first power. And then we do our second derivative there over 2 factorial, and this is squared. And our third derivative over 3 factorial, and so on, until we get to our nth derivative, n factorial, and that's raised to the nth power. Cut it off there. What's the next term? Well, the next term would be the n plus 1th derivative over n plus 1 factorial quantity to the n plus 1 power. Now, here's where I'm just a little sketchy. To me, I know there's a z there, don't let it freak you out, just ignore it for a minute. To me, this looks like my next term. They're calling this the entire remainder. That's the one thing that I'm just foggy about. To me, this appears to be one more term after this one. But they're calling this the entire remainder. Everything that got cut off. Okay? So, think about how you would express your next term. It would be your next derivative over the next number in the factorial, and this would be raised to the next power. Okay? And then we'll talk about what does z represent. You already know what c is. C is where it's centered. So just kind of get used to this because you're going to have to reproduce it quite a bit. But I mean, it shouldn't be hard because you're used to making these polynomials. You're used to doing this process every time. You just need to kind of think ahead to the next one. Alrighty. And what they're calling this is this, how do I say this? This is going to be our error. This is going to be the maximum that our error could be. We're going to look at that next term. We're going to figure out what's the maximum that our error could be. We're not going to necessarily figure out, oh, the error is. We're just going to figure out how bad can it be. The only problem is, we're going to know this. We're going to know this. we're not going to know the actual value of the whatever derivative. This is still going to be an unknown. But in every case, we can determine what the largest value of this expression would be. And if I can say, this is as big as this is going to be, and I know this for a fact, and I know this for a fact, this is the biggest that this is going to be, then I can say, okay, thus, I can tell how big this is going to be. And I can say, this is my maximum. My error has to be smaller or equal to that. Okay. I think I'm going to work backwards in these notes, even though example 3 starts with a proof. I just want you to kind of see how this flows, okay? I want you to see how the concept flows. So here's what we're doing. We're supposed to prove that this converges to sine x for all x. So this is what the series looks like, written out. This is that Lagrange error bound, the remainder. Okay, so talk about that in a minute. This is my whatever derivative. Converges to sine x for all x. This series is centered at 0, so I'm going to sub in 0 right here. So I just rewrote everything, subbed in 0 right there. That's what this now looks like, okay? All right, so here's the thing. Check this out. Look at the function that was mentioned in the problem. The function is sine of x. Think about all of your derivatives of sine of x. So we've got sine of x, derivative, cosine x, derivative, negative sine, derivative, negative cosine, derivative, sine, derivative, cosine, derivative, you know? So in every case, all my derivatives are a trig function, either sine or cosine. How big can those derivatives be? If your derivative is either a sine function or a cosine function, what is their maximum value? So, ready for this? Same. Think about the maximum value that any of those derivatives could be. Once I figure out what the maximum value is, I can say, okay, now whether this turns out to be positive or negative, I don't care. I'm going to absolute value it. My error has got to be less than or equal to this. It was equal to it if I knew exactly what it was. It not knowing exactly what it is, I'm going to turn this into an inequality and absolute value it so I don't turn out with a negative. Okay, so I think many of you have come up with the maximum value for any derivative of sine of x. The maximum it could be is 1. So here's what we're left with. Our remainder, or our error, is going to be x to the n plus 1 over n plus 1 factorial. What is that? What is x to the n plus 1 over n plus 1 factorial? Remember, we want x to get really large because we're talking about a series here. We're talking about a series. We want n to get super large. So if I send n to infinity, I get this over this. This one outstrips. So my limit is 0. What's that saying? My error, the difference between the two, the difference between the function and the polynomial, is approaching 0. Okay, so I wanted to do that one. I know that was a proof, that was a little weird, but I wanted you to see how we go from the whatever derivative. I don't know what it is, but I think I can pin it for a maximum value. I think I can narrow it down and say what its maximum value is. So I'm gonna absolute value that, so we're not dealing with a negative, and our error, our remainder, is going to be less than or equal to whatever that is. Okay, now let's back up. Let's see, which one do I want to do first? I think I'm going to do this one first. This is example 5. And we're only using the first two terms of the Maclaurin series, centered at 0. ln 1 plus x. We're approximating f of 0.1. Do the error bounding both ways. Okay, so hang on. Before I do that, I just want to kind of give you an overview. This is our function. And just for fun, I plugged in 0.1 to see what I would get. And this is what I got. And then it said use two, what did it say? Yeah, it says use the first two terms. So I grabbed that little table. Here's the first two terms. And then I was curious, okay, how close was my polynomial? I just wanted to see what it gave me. And there it is. That's what it gave me. Not bad. Okay, let's look at the error bound. When I write my error or my remainder, it's capital E or capital R with n here. Remember, n is how many times we did this. Okay, so since this was my second order polynomial, I'm using a 2 here, but I'm looking at the next term. So this would be the n plus 1th. And the alternating series error bound says my error is always less than that very next term. Well, what is that very next term with 0.1 plugged in? It's 0.0003 repeating. So oh, yes. Sorry, I spaced for a minute. I was like, wait, it's not. It's not within that. I was thinking 31018 was bigger than 0.3 repeating. Sorry. Whew. Got me on that one. Okay. So let's look at this using the Lagrange error bound. So I wrote it out again. And in this case, I'm using the second order polynomial. So this is a 2, which means this is a 3, this is a 3, this is a 3, and it's Maclaurin series, so C is 0, so that just kind of went away. All right, now, what is Z? Z can be anything in our range that we're talking about here. So by range, think about where's the series centered, and how far out are we looking? So the series is centered at 0. How far out are we looking? Well, we're wanting it to approximate it at 0.1. So we're only going from 0 to 0.1. That's our range for z. All right, so kind of a recap on what I just said. C is 0. This is where it's centered. How far out are we looking? Well, we're wanting x to be 0.1. That's it. That's all we've got. That's our range for z. So what I need, can I get the largest value of the derivative? Third derivative. What's the largest value the third derivative could be if c is 0, x is 0.1, which means z is somewhere between 0 and 0.1. Third derivative. So what I did is I came over here, wrote out a few derivatives really quickly. Here's the function, here's the first derivative, here's the second derivative, here's the third derivative. And then I took my third derivative and said, okay, I don't know what this is supposed to be. But z is somewhere between 0 and 1. This number has to be somewhere between 0 and 1. What's the largest value that this derivative could be? Well, I don't know. I'm going to try them both. What's the value of my third derivative at 0? It's 2. What's the value of my third derivative at 0.1? It's approximately 1.5. So this is the biggest this is going to be. So here's what I did. I replaced this numerator with a 2. That's as big as it's going to be. That was already there. I replaced x with 0.1 like it said in the problem. We're evaluating this at 0.1. So that's a 0.1. And since I don't know it to be exact, I don't know it to be exactly 2, but I said this is the biggest it's going to be. So I changed my equals to now my remainder is less than or equal to, and then I put parentheses around it so I don't have to deal with a negative. Did the math, and I got 0.0003. Repeating. All right, one more. And if you're still fuzzy on this whole derivative thing, we're going to look at it one more time. Next one. We're looking at a second order Taylor polynomial for f of x. Never tells us what f of x is. Have no idea. Don't know. Don't care. We're centering it around x equals 2, so c is going to be 2. I know that doesn't matter if it's positive or negative, but the third derivative is less than 2.3. And that works for everything within this interval. Notice this is where we're centered. This is how far out we're going. This is where we're centered. This is how far out we're going. Show that this, okay, this is just error, is less than 0.05. All right. Don't know what this is, don't care what it is. Here's our polynomial. I really don't know what the polynomial is, but if I were to build it, you know that I would find f of 2, and then I would find my first derivative at 2 over 1 factorial and make this to the first power. My second derivative at 2 over 2 factorial raises to the second power. And I'm calling, and see this is where it still gets me, I'm calling the rest of it my remainder. The error. Because if all of it is a perfect representation, then the amount that I disregard is the difference between the two. And this is the amount that I'm disregarding. So just keep in mind, this is our error. This is the true value minus our approximate value. And that's what it's saying to do. It's saying show that this is less than 0.05. So I'm going to show that R, capital R, is less than 0.05. So here we go. I've written it out. You should be pretty familiar with it. I'm using a second order polynomial. So this is a 3, this is a 3, this is a 3. I think you all know what C is going to be. That's the easiest one to know. C is going to be 2. X is how far out are we going? So that's part of your interval right there. Better start writing some of this down. C is 2. X is 2.5. Thus, Z would have to be in there somewhere. All right, so we knew we had a 3 factorial on the bottom. X is 2.5, C is 2, that's to the third power. This is my third derivative. What's the largest this can be? What is the largest my third derivative can be for some X value in my interval? What's the largest my third derivative can be? Well, it tells me that right here. My third derivative won't be bigger than 2.3. Will not be bigger than 2.3. That's the maximum value for the third derivative. Now, put it in absolute value, but I don't think we need them because I don't think that's ever going to be negative. And I can say that my remainder will be less than that because it was a less than sign up there. Do the math. Oh, sorry, hold on. Bad notation. That's a 2. It's a remainder from my second order. The rest of them were 3s. So R2 I got is less than 0.048, which happens to be less than 0.05. There we go. Good luck with this. I hope you don't have any questions. Nah, it's okay. We'll work them out together.